If we looked at the Lewis structure of methane, we would assume that we had 4 bonds at 90 degrees, because each hydrogen is oriented at 90 degrees. We would support this by saying, well, we're overlapping an s orbital from the hydrogens with the p orbital of the carbon and the s orbitals of the carbon. And we'd say, oh, well, these hydrogens are both positively charged. They have an electron density between them that's attracting them to that carbon. They're going to orient themselves to minimize electron pair repulsion, the electron repulsion of that bond, and so they'd minimize that by being at 90 degrees from one another. However, when we look at methane, methane actually, through experiments, is shown to have a different bond angle, the angle between 2 terminal bonds, a different bond angle than 90 degrees. Oop. It actually looks something like this, and I actually did that on accident, but it works out well. Where the bond angle is about 105 degrees. So now we have to figure out why that is. And the simple answer is because when carbon forms a bond, a covalent bond, it has to adopt a different electron configuration than its normal 2s, 2p orbitals. This change in its orbital configuration is called hybridization. And it's all about minimizing electron pair repulsion. The theory behind hybridization is the VSEPR theory, which stands for valence shell electron pair repulsion. So when I have s orbitals combining with p orbitals, remember that there is only one s, it's big and circular, stands for sharp. The p's are dumbbell shapes and can align along the 3 axi of a 3-dimensional plane. You can align along the x-axis, which comes into and out of the screen. You can lie along the x-axis, left and right, or the y-axis, top and bottom. In order to minimize electron pair repulsion, the s orbital can hybridize or combine with a p orbital to form a completely new wave function. This hybridized orbital is simply named after the two of them. An s and a p come together to form an sp hybridized orbital. And if you're ever on Jeopardy and never asked, it looks kind of like a mushroom with a large electron density region above and a little one below. And it can orient along each one of the axes. I've shown this one on the y-axis. You could have it on the x-axis with the less dense region on this side, the smaller circle over here, big protrusion over there, or on the z-axis coming into and out of the page. Now, electrons and atoms don't naturally do anything for just because they feel like it. There is an energy payoff, and systems always tend towards their lowest energy configuration. So what is the system, or what is the bond gaining by hybridizing? Well, if we looked at the electron configuration, or the electron orbital diagram of carbon when it is unhybridized, it would be all of the green arrows. However, when it forms an sp hybridized orbital, it combines the p and the s into a lower orbital. So while the s's actually gain energy, the p's drop down. Also, you'll notice that there is now no pairing, and therefore is more stable or has less energy with those electrons. Just as you can have s and p hybridized orbitals, you can also add in other sublevels, such as d. We will not go past d, and I do not have a pictorial representation of one. Just take my word for it. You can have d hybridizations, which you'll see when we get to the octahedral. The shape of a molecule will change based on its hybridization because it will try to minimize the electron pair repulsion. Now there are two types of geometry that deal with the shape of a molecule. There is the structural pair or electronic geometry, and there is the molecular geometry. We'll focus on the former, on electronic geometry first, and then we'll go back and clear up molecular geometries. Ooh, I'm trying to find, sorry, small problem with the pausing mechanism. The first electron geometry is linear electronic geometry. And to determine the hybridization, you simply count the sites of electron density. So simply the number of sigma bonds and lone pairs. So if I have something that has one sigma bond, or one sigma bond and two lone pair, or sorry, one sigma bond and one lone pair, that's two sites of electron density. Therefore, I need two letters when I name the hybridization. So two letters would be S and P. You can only have one S, and we'll take one P to do it. Now, when you explain why this is the electron geometry, you need to talk about the electron sites of electron density. Please never say, well, I have two sites of electron density, therefore I need two letters. That is not an actual reason. You would say there are two sites of electron density, therefore an S and P orbital must be hybridized, giving me an sp hybridized orbital. And no matter which way you cut it, if it is linear, it means it's a straight line. The bond angle, the angle between one terminal atom and another, is going to be 180 degrees. So the top picture would be that of something that is diatomic. The bottom would be between, say, like carbon monoxide. Triple bond, however, one lone pair, one sigma bond on the carbon gives you sp hybridized or linear electron geometry. If I have three sites of electron density, that means I'll need three letters. So you can have up to three P's, so let's take another P. That gives us sp2 hybridized, that's three letters, sp and p is three. And the shape is called trigonal planar. Now my picture there is kind of rough, so how about a ball and stick model? And I realize this one's kind of rough as well. But all three of these yellow balls lie in the same plane. And there should be 120 degrees between them. And this one has apparently ventured off on its own. Stay right there. There we go. 120 degrees. This would be a trigonal planar. Three sites, 1, 2, 3, of electron density. Therefore, trigonal planar. When you have four sites of electron density, four bonds to the central atom, or the electronic geometry is tetrahedral, meaning that and therefore the hybridization, you need four letters, so we'll grab all three P's and an S, P, 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 and S, that's four letters, so sp3 hybridized. And the bond angle becomes 109.5. This is the common tetrahedral shape, where you have three below and one above. I realize putting that directly under the camera is a bit of a mistake. Tetrahedral. If you add an expanded octet, meaning you can have 5 bonds to the central atom, you have a trigonal bipyramid. And since I have 5 sites of electron density, I'll need 5 letters for my hybridization. So 5 sites, we'll grab all 3 P's, the X, Y, and Z. We'll grab the S, that gives us 4. And since we're pulling in the expanded octet, we're going to add in the D sublevel. So DSPPP gives us 5 sites of electron density. So DSP3 hybridized would be trigonal bipyramidal. And it's called trigonal bipyramidal because it's like having a three-sided pyramid, one on top of one another. Bring this up here. Where the bond angle between the top, this one coming out of the screen, and the one next to it, this is 90 degrees. However, between these three that fall along the same plane, there's only 120 degrees. Apparently I am not much of an artist because this looks kind of crazy down here. But if you are DSP3 hybridized, the shape is trigonal, the electronic geometry is trigonal bipyramidal. Lastly, if you expand your octet even further to have 6 bonds to the central atom, you have an octahedral shape. 6 sites of electron density, therefore we need 6 letters. S and the 3 P's gives us 4. We added D to give us 5, so let's just pull another D. So D2, sp3 hybridized, is an octahedral electronic geometry, or structural pair geometry. This is an octahedral shape. All of the bond angles are 90 degrees between each terminal atom. No matter which way you lay it, you have 4 bonds that lie in the same plane. Now, when we started talking about hybridization, I said it's the number of sigma bonds and lone pairs. And all of the electronic geometries are based off of simply that. Number of bonds, sigma bonds, and number of lone pairs. And that'll give you the electronic geometries. However, molecular geometries are the geometries that each atom is in correspondence to the central atom. And lone pairs kind of mess this up. Anytime that your number of lone pairs is 0, your electronic geometry and molecular geometry will be identical. When you add lone pairs, it's going to change the shape. Essentially, it's like lobbing off one of the bonds. The electronic geometry is still the same, and the hybridization stays the same. However, the shape of the molecule is going to change, and the lone pairs are going to alter the bond angles. The only one that is unaffected by number of lone pairs is a linear shape. The linear hybridization, if you're diatomic or if you're polyatomic, the hybridization will stay the same for anything that is linear. Trigonal planar, if we took off one of the bonds off of trigonal planar, we would end up with a bent shape or a V shape. Renee calls it a V shape. I have always seen it been called a bent shape. And you replace one of the bonds with a lone pair. There are still 1, 2, 3 sites of electron density. Hybridization stays the same. However, that lone pair, since it is only bound, or since they are only attracted and drawn by this nucleus, they are going to repel the electrons in the bond between the central atom and the terminal atoms, and they will push that bond that bond angle closer together. So whereas before, when we were trigonal planar, we had a bond angle of 120 degrees. By adding a lone pair, they take up more space. They repulse the electrons, the bound pairs, and decrease the bond angle. In a tetrahedral shape, hybridization is sp3 hybridized. Bond angle is 109.5 degrees. If you take off one of the bonds and replace it with a lone pair, like in the case of ammonia, you form a trigonal pyramid, because you could make a pyramid with just 3 sides. And again, that lone pair is going to take up more space because it is not being drawn by 2 nucleus, it's only being drawn by 1. Lone pair takes up a lot of space and repels the bound pair and decreases the bond angle. So the bond angle of, say, ammonia would be like 107.5. If we remove another bond and replace it with a lone pair, like in the case of water, and I'm sorry my lone pairs aren't here, let me fix that really fast. There we go. We now have 2 lone pairs, but we still have 4 sites of electron density. Hybridization stays the same. Those 2 lone pairs are going to push that bond angle and repel those bonded pairs even more, and the bond angle is going to decrease substantially. So in the case of water, one of the most commonly known bond angles, water is 104.5 degrees because those 2 lone pairs are going to repulse that bond so much. In the case of the trigonal bipyramid, where we started with 90 degrees and 120 degrees along the same plane, 5 sites of electron density, therefore dsp3 hybridized. When we remove one of the bonds and replace it with a lone pair, we end up with what's called a seesaw, where we have 2 bonds that exist at 180 degrees, and they have the lone pair between them. And then we have 2 bonds that are at 120 degrees, and between the 2 that are 120 degrees existing in the same plane and the 180 degrees, which exists in a different plane, there's 90 degrees. If we add another lone pair, we end up with the T shape, which looks like a T, and all the bonds exist at 90 degrees. And yes, it is true, we could take off another bonded pair and replace it with a lone pair, and that would give us back to the linear shape. However, the hybridization is still the same. The electronic geometry is still the same. The structural geometry, those are their structural pair geometry. Those are synonymous terms. They are still the same. This would be trigonal bipyramid. The molecular geometry may be linear. However, the hybridization will stay the same as the trigonal bipyramid. The octahedral, the most complex one we'll see, 90 degrees between all of its bonds, 6 sites of electron density, D2sp3 hybridized. We remove one of the bonds and replace it with a lone pair, we get a square pyramid as the molecular geometry, because you could create a true 4-sided pyramid. Remove 2 of the bonds, you end up with a square planar. This is like trigonal planar, however there are 4 now. The lone pairs will orient themselves on opposite sides of the central atom, and that will maximize or minimize their electron pair repulsion. The molecular shape will become extremely useful to you when you determine bond polarity, which will be our next video. However, your most common question will most likely deal with the electronic geometry, so you need to keep those 2 straight in your head. Electronic geometry or structural pair geometry is simply based off of the hybridization. Count the number of electron sites for electron density, determine the number of letters you need, and you've got the electronic geometry or structural pair geometry. Once you add in lone pairs, that's when you need to start looking at bond angles, the molecular shape, the molecular geometry.